Okay. All right. So I'll again ask this question. Did you have any doubt in week 4 and 5? Do you have any doubt? If not in the content, do you have any doubt in the assignment? So there was week 4 had assignment, right? I don't know whether you have any doubt or not. Did you have any problem solving this question?
Sir, in the answer key uh, that will be
Mm-hmm.
provided by the NPTEL,
Mm-hmm.
there are two questions with that have same answer. Like I
Which
don't
two
know,
questions? The
two
first
questions.
two?
No, no, like seventh, like zero pole location, zero location, non-dominant zero location. Yeah, that one.
This is 20 and 20. Your answer should be in 20 to 44.
Yes, sir. And in
Oh,
the
ninth question also.
yes, sir.
What are the question?
So, so in the answer key, they have, but in the original solution, in the while marking the question, they have taken different range, like, but the range should be same for the questions.
Okay, I've not solved this myself. So this is something that you have to this issue you have to raise with the, because I do not look at that. Okay, I will not be able to help you in that. This is a separate administration which I am not a part of. This issue you have to raise with them. But yeah, so I understand. If you, I mean, my question is that if do you have any doubt in this other than, I mean, the answer being wrong or whatever? Do you have a doubt in the concept of this question? I'll be able to help you with that in that.
No, sir.
Okay, all right. If not, then what about week 5? It was a question was very much alike. So what about this? Anybody? Any doubts in this particular week?
No,
Week
sir.
5?
No, sir. Sir,
Okay.
yes, sir.
Yes.
In this week, there is some mistake, like from their end.
Week 5 or week 6?
Week five, sir. Yes, sir.
Yeah, what is the problem?
So question number 7
Hmm.
and question number like non-dominant pole zero.
Again, if you are sure about that,
Yes, sir.
uh,
It's question number 6 and 8.
question
The
600.
yes, sir. Because
Yeah, I
the
understand. See, that's what I mean. I'll not be able to help you with the regrading thing because that is something which other people look after. I'll not be able to help you. You have to raise this concern with the competent authority. I do not have the jurisdiction. Okay, so this I'll if you have a doubt in the understanding of question or how do you solve it, then I can help you right now. So this you
no,
have
sir.
to raise this issue you have to raise with the authority. I guess you know how to do it. I don't know. Do you know how to raise this issue?
No, sir. No, no, sir.
I Okay, probably you have to mail the instructor or maybe the TA for this course. I don't know. Or maybe in the Q&A you can ask this. I have no idea. Okay.
Okay,
So
sir.
this is not something which I will this is not something which I have to do. This in fact I do not even have the jurisdiction for doing this. All right. So you had I mean concept wise everything is clear, right? Assignment 4 and 5, no
Yes, sir.
issues there. Okay, good. Let's move ahead to week 6. Okay, so this I have to discuss anyway. All right. So anyway, since I was not here for the 2 weeks, I'll anyway just keep mildly refresh the things that were covered. So the two main things which were covered in the 3 weeks, basically, including this week 6 also. So 4, 5, and 6. So we mainly learned about compensation, right? The compensation thing which was covered. That is what we learned. So I'll ask you this question. And don't worry, I'll have sufficient time to solve. I mean, I'll not solve the problems here. Okay, the problems here that I have to discuss today are simply the same problems that you have in your assignment. I will only discuss the key points Basically, that will help you solve the question. I mean, this is not something that was discussed in the lecture, so I'll cover that. All right. So let's talk a little bit about compensation. Okay. So what do you understand by compensation? Why do we need compensation? Come on, guys, quickly. You can answer, and I will be moving on. Any one of you, please answer. What is meant by compensation? Why do you need it?
To shift the pool location.
Yeah. And what is the importance of? I mean, why do we need to shift it?
So because like if the poles are very close to each other,
Okay.
so at omega u we can't achieve the linear like minus 20 dB decade slope. So that will affect the stability. So if we apply a compensation, then we can separate a pole apart. That and hence we can maintain a first order like first order
Hmm.
like body plot and maintain a minus 20 dB slope at
And
around.
why is minus 20 dB very important?
Sir, it, it it's an ideal integrator. Like the slope of the ideal integrator around omega u is minus 20 dB.
Yeah. So what is the? Yeah. I mean, you are right, but what is so holy about? What is the problem with minus 40 dB per decade? What happens?
Uh, uh,
Yes, it is correct that it is an ideal integrator, but what happens if you do not get an ideal integrator? What happens if you have something of this kind?
it will affect the stability.
Of course. So as we learnt in the week 3, right? Week 3, I think, that any delay in a feedback loop will cause instability, right? So any delay in the feedback loop causes instability, isn't it? So delay in negative feedback causes what? Instability. And what is the uh, equivalent of delay in a circuit? I mean, how do we get delay in circuits mainly? We get it by? We get it through
Poles.
poles, right? Basically, LHP, left right half plane poles, and right half plane zeros, right? This is how we get the delays, right? Correct, no? Okay. So basically, that's why we do not want delay ideally, right? We do not want a lot of delay in the system. So, but anyway, if you are integrating, if you are having an integrator in a system, if you are having an integrator in a system, so you are bound to get some delay, right? An integrator has an inherent delay, isn't it? An integrator has an inherent delay. It will always have a delay. So you are bound to get some delay, but that we are okay with. Okay, so that delay we are okay with that delay in a feedback loop. What we are not okay with is excess of delay after integrator also. So that is why we do not want the second pole. So a better way to visualize this is in the Nyquist plot, isn't it? So we know that in the Nyquist plot, sorry, not Nyquist plot, but sorry. So this is the, if you plot the loop gain and the S plane, sorry. So this is your j omega and this is your sigma. If you just recall, so what did you do? How did you do it? So let's say you had a loop gain of this kind, some a divided by 1 plus s over p omega p, right? So if you have this kind of a loop gain, how will it look like? Rather than minus. So how will it look like? It will look like something of this kind, right? We start from here and then how does it look like? Correct? So this is how it will look like for a single order system, first order system, if the loop gain has a first order response. However, if the loop gain has what? This kind of a situation, let's say it has another pole. Hmm, let's say that it has another pole. How it will look like? It will also start with the same place, I mean almost the same place, let's say, and then it will do this, isn't it? It will do this, and then it will, yeah, so this is basically the image of this. So, right, and the issue is that we have the condition for stability is that is what? Tell me, what is the condition for stability?
It don't enclose -1, 0 in clockwise direction.
Yeah, so you should never. So let's say this is our. So basically, what is the point? So let's say this is your -1, 0 point. Sorry, this is, let's say, -1, 0 point.
So the center of the circle will be -0, 0.
Come again?
Center of the circle should be 0, 0.
Okay, okay, sorry, you are right. Yeah. So this is -1, 0, right? So what is the point is that you never have to, should never enclose. So this is the direction that we are going, right? By the way, so this is the direction that we are going. Should never enclose this point, isn't it? So for a second order system, this is never going to happen. So even if you have this 40 dB per decade slope, if you only have two poles in the system, is your system ever going to become unstable?
No.
It is never going to become unstable because you will never ever cross this point. You are never ever going to enclose this point, right? Whatever
Yes.
you do, it will always go and do this, isn't it? So the problem is what? Why are you then afraid of this 40 dB per decade slope? Tell me. Why do you not want this 40 dB thing? 40 dB per decade thing?
Because there will be a negative component. That's why.
What negative component?
No, no, no. Is plain.
The problem is that if you have this kind of a response, if you have this kind of a response, the thing that will happen is, let's say it's a unit, this system is, let's say this is the amplifier, okay, and you have connected it in negative feedback, let's say. So let's say this is your V in, and let's say this is, and let's say this is your V out, and let's say this amplifier, this overall feedback has this kind of a response. This feedback here has this kind of a response, let's say. So what is going to happen? If you give a unit step here, what you will see at the output will be, because of this 40 dB per decade slope, what you will see at the output, you will see terrible ringing. I mean something of this kind. The output will settle with a lot of ringing, and this ringing will prolong for a very long time. So you will see something of this kind, and only after a very long time this ringing will stop. Is that point clear?
Yes.
Yeah, and this is not good because in a lot of systems you do not want this. You want the system to settle very quickly. It should settle very precisely. You do not want this ringing. This is not this is not good. Okay. And the other probably bigger reason is that bigger problem is that, you see, we could have let's say we could have lived with this ringing also. The bigger problem is that you will never have this 40 dB per decade only. Okay, you will never have only two poles in the system. There will be a lot of poles that will come at a very high frequency. Okay, so you will always have more than two poles in the system. You will never have that only two poles in the system. So you will have that more than two poles in the system, which can make, which if something wrong happens, which then basically your system basically this particular thing can happen. Okay, it can cross this particular -1 comma 0 point in this manner, and then your system will become unstable. You get my point? So in any device that you will have some inherent a lot of poles basically. For example, let's say you have a MOSFET. Okay, so now that you know, I think in this week only you have learned a little bit about MOSFET and all devices that you have. So let's forget even MOSFET also. Let's take resistor for example. Okay, let's say you draw on a piece of paper this kind of a RC circuit, right? This is the RC circuit that you draw, and you say that it has only one pole. Correct? Now, the moment you go ahead and implement it in an IC, what will happen? The R will be implemented using some metal, right? Some metal or poly layer, isn't it? So this you have already learned, right, in week 6. So that is why I'm discussing this. I would like some yeses and nos from you.
Yes, sir. Yes, sir.
Yeah. So this is your R. And how do you implement C? C will be some big plate, and then there will be some bottom plate also, right? Correct. There's some bottom plate. So it has some top like this, and it will have some bottom. Correct. And then you go ahead and connect this and connect this. So what happens is this R that you say here, it is like distributed R, right? A lot of R distributed with each other, and in between from this there will be some parasitic capacitance always to ground. Are you getting my point?
Yes, sir.
So this is not a single this R cannot be a bulk R. This is not a bulk resistor. It is distributed kind of, right? And between the metal layer to ground to substrate, you will always have parasitic capacitances everywhere. So it's kind of
So
a
there will
distributed
be
thing.
infinite number of pole, and they
Of
will be
course,
on
that's why.
very
Correct.
higher frequency.
Correct. There will be infinite number of poles here, and they will happen at, I mean, that is why it will happen at very high frequencies, but there will be a lot of poles. So this is like a very exaggerated example, but I'm saying that, so what happens is, in a system you will never have this only two poles. You will have more than two poles always. So you want to make sure that around this point you are always safe. So whatever happens, if even if the system is so you do not know how the IC will be fabricated and come back to sent back to you. IC fabrication can have a lot of uncertainties. So do not know that. So you want to always be sure that your IC, even if it is not fabricated properly, it works. So that's why you always want to make sure that around the point where your around the unity gain frequency, your slope is as close to ideal as possible. Understand? And what is the ideal slope? It is -20 dB per decade. Correct?
Yes, sir.
Yeah. So that is the point. So that is why you make sure that it is -20 dB per decade. So now, since you have these two poles close to each other here, this system is going to be very close to instability. So what do? You go ahead and compensate it. So what are the ways of compensating? I think there are three ways to compensation, right? You have learned that. What are the three ways of compensation? Come on, quickly. What are three ways of compensation?
Miller compensation.
Oh, good, good. Miller compensation.
Feed forward.
Good. Feed forward. What is the last one? So last one is probably the most simplest one. I wonder why you didn't start with that. What is the last one? You have even solved assignment questions on that last week. Tell me, what is the last one? It is dominant pole. Okay. So I guess you know this. You know this. What is dominant pole compensation?
Make one pole dominant and like
Yeah. So
another
this is
zone
probably
of
the simplest, and this is like this is probably the simplest architecture. I mean, the simplest thing that you can do. There's no, I mean, it does not. It's a no-brainer kind of. You do not need to invest a lot of brain power to this. It's the simplest thing. It's the most brutal, brute force thing that you can do. Just have to make sure that so simply you see that there are two poles here, right? One pole is here and one pole is high at a higher frequencies, right? So what do you want to do is you make sure that this pole here is made dominant. So what do? You shift it to very low frequencies. Got it? So instead of this pole appearing at this point, you make sure that this pole appears at this point. So let's say it appears at this point. So what will happen? Let me use a different color. This is not good. Use this color. So let's say this pole appears at this point. So now what will happen? At this point only it will start going down. So my drawing is probably not very good. Okay, this will not do justice. Okay. Hmm. So let's say you have this pole here. Now, right at this point only you start going. And now you see that your second pole is later, right?
Yes, sir.
Correct. So this is dominant pole compensation. This is a no-brainer. What is the problem with dominant pole compensation? You can
like
quickly understand.
omega u unity gain frequency decreases.
Unity gain frequency decreases. Good. What else? So let me just point it out here. Omega u decreases. Good. What else?
Output resistance is low.
Output?
Resistance. So
Mm, well, that is not. So that is not. That need not be true. That is a very subject. I mean, specific application specific thing. That is not. That need not be true. So what else? Omega u decreases. Yes, correct. What else? Acha, tell me, how do you make a pole dominant?
Speed decreases.
Yeah, yeah, true. Omega u
It's
decreases
a
means speed
by
decreases, isn't it? I mean, what is the significance of omega u?
uh, it's the rate at it's the rate of indication.
I mean, yeah, correct. It is you can correlate it in that manner. Yes, it signifies the speed at which your integration happens. Correct, correct. So if omega u is lower, which means what? Your system is integrating slower, right?
Yes,
So it
and
means your system is ultimately slow. Correct. So omega u directly correlates to your speed.
yeah,
Got it? Good. What else? So that's what I asked this question. How do you reduce the pole frequency? How do you reduce the pole frequency?
mm,
So this pole you have shifted to this point at a very low frequency. How will you do that? Okay, let's do an example. Okay.
Yeah. Increasing the capacitance.
Good, good. So for example, let's say you have this GM. Okay. So understand what is GM, right? This symbol,
Yes.
what this
That's
symbol
conduct.
means? Yeah, it's a transconductor, right? So let's say you have this plus minus, and so let's say in between these two, you apply a V in, and here is the current, which is equal to GM times V in,
We
right? Yeah. And you have this capacitor C1, and then let's say you have another GM2. Let's change the color, it's not good. And let's say this is okay. So this is your C1 and this is your C2, right? And let's put some resistance also here. Let's call this R1 and let's call this R2. So what are the two pole locations here?
Um, 1 upon R1 C1, 1 upon R2 C2.
Correct. These are
yeah.
two pole locations. Now tell me, so let's say again, you want to reduce this pole. You want to make sure that this pole is dominant. How will you do that? You want to reduce P omega P1. How do you do that?
Increase C1.
Yeah, there is also another way, right? Increase R1. That also you can do right now.
Uh,
But I have not said it explicitly. This R1 is not something which you put
it's
yourself. This is
control.
the this is the output resistance of GM. Okay,
Yes.
and it is not in your control.
And C1, C2 is our under control only.
Yeah, this is under your control, C1 and C2. So basically, what will you do? The only way you can reduce this is this omega P1, that is the pole frequency, first pole frequency, is by increasing C1, right?
Yes.
And as it turns out, this is the most inefficient way of reducing the pole frequency. I mean, this
Yes.
will require a very high value of capacitance to shift the pole to a very low frequency. Got it?
Yes.
Understand? So basically, now I'll tell you will be able to appreciate this statement more when I talk about Miller compensation. So tell me, so these are the two problems, by the way. In that omega u decreases and you require a very large capacitance. Okay. Okay. Now let's talk about Miller compensation. So how does Miller compensation work? Again, going back to this curve, this magenta curve. How does Miller compensation work here in this example?
Which curve, sir?
So how do you
There will
compensate
be
it?
a feedback capacitance in second stage for mirror compensation.
So how will you do this? You will put a capacitance like this, right?
Yes.
So let's call this Cm. This is what will you do, right?
Yes.
So what happens when you put a mirror capacitance here? So why is this called mirror capacitance?
Because from input side it looks like more capacitance than it is there. It's
Hmm,
multiplied by its gain at
correct.
first.
It's multiplied by which gain?
Second stage gain.
Yeah. So what happens here is, what did we want, by the way? We wanted to make sure that the pole at this location is dominant, right?
Yes.
But what did we want actually? What actually did we want? We wanted to make sure that this pole here moves out of omega u loop, right?
Yes.
Moves away, right? Second pole has to move away. First pole has to move in this direction, right?
Yes.
So let me make a clear, good picture. Okay, so this is not good. Let's copy it and paste it somewhere. Okay, so let's remove this now. Yeah, what did you want? You wanted to make sure this is omega p1, this is omega p2, and this is your omega u. What did you want? You wanted to make sure that our second pole has to move away out of omega u, right? And the first pole has to move here in this direction, right? This is what we wanted,
Yes.
ideally. So the main objective here is to make sure that the gap between these two poles has to increase, right?
Yes.
And earlier in the dominant pole compensation, what were we doing? We were not touching the second pole. We were only making sure that the first pole is moving away, right? That is
Yes.
what we were doing. But don't you think it is more inefficient? I mean, the more efficient way would be to move both the poles apart, isn't it?
Yes.
Correct. So this is what is done in Miller compensation. What Miller compensation does is it makes sure that this pole, sorry, yeah, it makes sure that this pole here is increased. Its pole frequency is decreasing. And how does it do that? It makes sure by increasing the capacitance looking at this point, right? At this
Yes.
point, the total capacitance is multiplied by the gain of the second stage. So capacitance increases a lot at this point, isn't it?
Yes.
However, what about this place? What happens here? This is a second pole, right? This contributes to the second pole. How? What about this?
It's got decrease.
This pole frequency increases, right? This pole
Yeah.
frequency increases, right?
Capacitance got decrease.
Capacitance does not decrease. No, 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 no.
Be-
Capacitance
Because
does not decrease. It's the conductance at this node. Okay, the pole happens because of some conductance divided by some capacitance. Okay,
Yes.
so what happens is the numerator here increases for the second point, isn't it? I mean, earlier what was the pole location on 1 over R2 C2, right? This was the pole location earlier. And what does this do now? This approximately becomes equal to GM2 by C2, right?
Yes.
After doing this, after Miller compensation, this approximately becomes GM2 by C2, isn't it? And mind it that GM2 is much. So how do you? So basically, this guy has to be larger, right? GM2 has to be larger. So when will this be larger than this? When GM2 by C2, this has to be larger than 1 over R2 C2. When will that happen? When GM2 R2 is greater than 1, right? Isn't it? What I'm saying here is that because of this Miller capacitance, we already saw that the first pole is decreasing in frequency, right? It is reducing. The effect of this Miller capacitance on the second pole location is what we already have. I mean, this is by the derivation that the second pole location is approximately equal to what? GM2 by C2, right?
Yes.
It is approximately equal to GM2 by C2. Now, I am claiming that this GM2 by C2 is larger than 1 over R2 C2. That is what is the claim. That is, I mean, only then will this pole move forward, right? Move in this direction. When
Yes.
earlier it was 1 over R2 C2, now I am saying that it is 1 over, sorry, it is GM2 by C2. And I am saying that GM2 by C2 is in this, it is larger than 1 over R2 C2. And
Yes,
when will
yes,
that
yes.
happen?
Got it.
When this
That's why
quadratic.
in pole location 2 we get GM2 on the numerator.
Yeah, this is correct. So this is by derivation. I am asking what is the constraint on GM2 and R2 for that to happen. So GM2 R2 should be greater than 1, right?
Yes,
So this is anyway true, right? Because GM2 R2 is what? It is the gain of the second stage, isn't it?
yes,
And you always want to make sure that gain is larger than 1,
yes,
because gain of unity is what? It is nothing. It is no gain. So you want to make sure that there is some gain. So that is why Miller compensation is a very efficient way of compensating, because for one small capacitance it actually splits the pole and send them both in the opposite directions. So what will Miller compensation do is, so if I want to just put it here, uh, yeah. So what will it do is, let's say it will again start here, and let's say this is first pole. This is the first pole. So this is the omega p1 dash after Miller compensation, and after that it will start doing this, and after that let's say this is the omega p2 dash. Got it? So in this way your omega u loop is not decreasing. So I have not shown it correctly here. Your loop, I mean unity gain frequency will decrease. Okay, so it is not shown correctly here, but you understand the point. What I'm trying to say here is that ultimately this will make sure that the distance between omega, the two poles, is
increased.
increased. Got it?
Yes,
And that is why it's the most efficient way of doing it, compensation. So this way your omega u is not compromised. So it's a very, I mean it is used for this will give you high speeds. Okay, and I mean capacitors here, caps are comparatively small. Now what about feed forward? What about feed forward?
The difference between number of pole and number of zero is one inside omega.
yes.
Yeah, correct, correct, correct. You are right. So how do you do that? Feed forward compensation. The point is that you can always compensate in another manner. So there is also another way, right, of compensating. So for example, if you have this, so one way we looked at, we make a pole very dominant. The other way was to make sure both the poles are split. Correct. These are two ways that we saw. The other logical way would be what? To make sure the only requirement is that at in at the around this frequency you have to make sure it's a 20 dB per decade loop gain, right? Sorry, 20 dB per decade slope, isn't it? Around
Yes.
the omega u loop. So that can also be achieved by, so let's say this these are the two poles. So this requires, so this can also be done using this, right? When this follows this, and suddenly at this point you again introduce a zero which
Yes,
does this, right?
yes,
So here, so this is a omega z, This is your omega p2, omega p1, and this is your omega u loop, isn't it? Correct?
Yes.
Yeah. So how does this work actually in this example? How does this work? How will you make sure that you introduce a zero? Hmm?
We will do feed forwarding.
Yeah. So what is that?
We introduce supply current of for the G naught and output capacitance that previously was drawing from the transconductor himself. So we will supply that current from feed forward.
This is what is has to be done, right?
Yes.
Your C1, this is your C2, and this is your. So let's say this is GM1, this is GM2, this is let's say GM3, or let's say GMF. So what will this do? This will. So now you have a simple straight path here, right?
Yes.
Which was earlier also, but now you also introduce another path, isn't it? And this is called a feed forward path. Got it?
Yes.
So this is a feed forward path other than the already present. Yeah. So this is basically the earlier thing, whatever you had, and this is the feed forward path which implements the compensation, which takes care of the compensation thing. How does this work? At very low frequency, what will happen? Tell me. At very low frequency, what will happen? The signal will prefer this path, right?
Yes.
This is also this is also clear from the from this Bode plot, right? At very low frequency, where is the transfer function? I mean, transfer function is following the magenta curve, right?
Yes.
So magenta curve is the transfer function of this slope, this first path, right? And the and this guy, the blue curve here is the final. I mean, overall transfer function, overall filters. Sorry, overall amplifiers Bode plot. Okay, so where is the for very low frequency? You can see that the amplifier actually follows the this path, right?
Yes.
So for simplicity, I will not use. I mean, for so let's understand the nomenclature here. So this guy here, this path is called the feed forward path. Okay, feed forward path. Okay,
Yes.
or you can also call it the fast path, and I will explain why it is called so. And this guy here, the one in red, this is called the slow path. Okay, all right.
Yes.
Okay, so at very low frequency, what path do we follow? We will follow the slow path, right?
Yes.
Okay, good. Now at very high frequencies, what is going to happen? We
It
can
will
see
follow
that
the next, but I mean, where only one pole is present.
it will follow
Below.
the feed forward path,
Yes.
isn't it? And it is also visible from this curve, right? It is
Yes.
deviating from this, sorry, it is deviating from the slow path transfer function, right?
Yes.
So what is happening here is that this, let's say this GMF, it will have a transfer function of this particular kind. Let's use green color. It will have a transfer function of this particular kind. Okay. So your magenta curve is the, this is the slow path, and this guy here is the fast path. Okay, you can see that at very low frequencies, sorry, at low frequencies, slow path is favored or dominant. At high frequencies, fast path is preferred, isn't it? And from this argument only you can understand why it is called why this path is called fast path and why the other one is called slow path. Can you guess now what is the reason? What do you think is the reason for calling the second one, this guy is the fast path and this guy is the slow path? What is the reason?
Because of its unity gain frequency.
Yes, I mean one way you can say that because it sets the unity gain frequency. See, whenever we say that something is operating at high frequency, it means what? What is high frequency? Frequency is the inverse of time, right?
Yes.
Time period. So if the frequency is high, which means time is very small, isn't it?
Yes.
So if something is operating at higher frequencies, which means what? It is naturally fast,
Yes.
correct? So you can clearly see that at very high frequencies, at very high frequencies, which path is favored? The fast path is favored, and that is why it is called fast path, because it is working at higher frequencies compared to the path that is working at lower frequencies. This guy is working at lower frequencies, and that is why it is called slow path.
Yes.
Okay, but what is the impact? What is the significance of this slow path? We can always say that why do we need slow path? We can always have fast path, right?
It's provide the gain.
Ah, good. So you can clearly see that the fast path gain is very small, isn't it? So gain is something which is set by the slow path, and that is why the gain and thereby the error that will be there in the system ultimately, that will be dominant, that will be set by the slow path. But fast path will make sure that the system settles faster. Okay,
Okay.
okay, good. So this is what I had to say about all the three compensation. One important thing that I missed was about Miller compensation. This was mentioned in the class, but I'll just reiterate it again. So in the Miller compensation, what do we have? We have one problem, right? What is the problem? What is one problem with the Miller compensation?
C1 should be low.
No, no, that is not a problem. I mean, why do you say that is a problem? Yeah, C1,
Otherwise,
sorry, C1 should be lower than CM. Yes, for that has to do with this particular approximation.
yes.
Okay, but there is another big problem with Miller compensation. What is that?
We make to like we we want GM2 will be higher. We we want GM2 will be higher. So if we construct a transconductor with high GM2, it will cause a higher power
Yeah,
distribution.
that is true. I understand, but I was talking about the zero problem, right? So you remember right half plane zero.
Yes, sir, right. Okay.
Yeah. So why does that happen? By the way, what is the location of this right half plane zero?
GM2 by C.
Right?
Hmm.
This is the pole location. Sorry, zero location, right?
Yes.
GM2 by CM. And why is this not a good news? This is not a good news, right? Why is this a problem?
It will contribute more phase lag.
Yeah. And what is the problem with phase lag?
So the
Loading will be there.
phase margin got decreased. Like
Yeah, so what is that? I mean, how do you, what is the significance of all of that? That is what I'm asking. Phase margin decreases, phase lag increases. So what is the, I mean, what happens because of that?
There will be ringing on the output. I mean,
Correct. So system becomes, goes closer to instability, right?
yes,
So you were trying to solve instability problem, but you added another problem, right? So this is
yes,
not a good thing. So, but people still do this. Why? If people still do this, which means that the problem is solvable, right?
yes,
Yes.
The problem is solvable, and what do people do to solve this problem? People add this register here. It's
yes,
called a zero cancelling register. I don't know whether this was covered in the class or not.
Yes.
yes.
This was
Not
covered
much.
or not?
Yes, we
Covered.
covered.
Good. So this is zero cancelling register. What is the value of this register?
1/GM2.
Yes.
1 over GM2. If you add this register, then your problem will be solved.
But
But come
it will
again,
add
yeah,
it will add one pole.
good. It will add another pole. So ultimately, it looks like whatever you do to solve, something else is disturbed, right? One more problem comes up. So this is always true. I mean, whatever you do to solve one problem, another will pop up. It's just that how you manage all the problems. So it turns out that this indeed works. I mean, uh, people do this, and this works because the poles and the zeros that come after this will come at a very high frequency, and that can be managed. Okay, all you want to make sure is that in the vicinity of this omega u at this point you should have a 20 dB per decade slope. Okay, whatever happens after this is not your problem.
Yes.
Okay. Hmm. However, I mean, one more problem is there. So this RZ, adding this resistor also has a problem. Can you guess what is the problem? And this has something to do with the fact that something to do with the process variations. Can you tell me what happens? Can you guess what is the problem? Why this particular uh, solution will not work very well in practice?
Because we can't match it properly.
Ah, correct. So this kind of this particular
One
thing,
upon two is not like
it
is
is
not.
not going to be, it is not going to hold very well because
Yes,
with temperature everything changes, and even if there is, even if you make sure the temperature is constant, you can, I mean, in the process there is a lot of variation, right? When you will
yes,
manufacture, there will be
To
a lot of
make
variations.
to
This
hold the
is,
exact equality, it will be difficult.
yeah, it is not going to hold. The equality is not going to hold very well. Okay, there will be some variation, and as it turns out that those variations are, if those variations are small, then you are kind of okay because if it is not perfectly cancelled, it will be. I mean, there will be some residue left, but that will happen at very high frequencies. So you are still good, but still, this is not a good idea. So there was a very old paper, 1980 somewhere, or maybe seven, no, 1880 something. There was a very old paper which solved this problem. So instead of adding this resistor, uh, that author did something else. And if you want to look into it, you can go back and refer to a famous technique called as Ahuja compensation. Okay, you can look at it. Ahuja compensation. All right. The paper is in 90. Paper was introduced in 1980 something. And so the reason that I'm saying is this because I'm a very proud. I, uh, I'm very proud of this because uh, Dr. Ahuja was the alumnus of IIT Kanpur. So that is why. Yeah, his full name is Dr. Bhupendra Ahuja. Okay, so you can go back and just refer to this. This is a very famous way of compensation. I'll simply give you an idea of how this works. If you remember, the reason for the zero was what? Tell me. What was the reason for having a zero here? Why was the zero appearing? Right up plane zero?
CM is there.
No, there is two path like
Ah,
forming
Yes.
so correct,
even
correct. So basically, you have what? You have
one
two
is
paths. One is in this direction. One is from this direction, right?
Yes.
So these two paths you have. And if you make sure, but what do you want actually? You want to make sure that this capacitor is there and this capacitor has to be amplified. And how does the Miller compensation actually work? The capacitance that is appearing here has to look like it is amplified. How does that amplification work? I am digressing a little bit, but this looks interesting, so I'll just speak a little bit about it. This is really important. So let's go a little bit about talk a little bit about Miller effect. So let's say you have a amplifier A of gain minus A, sorry, and this is your capacitance. So what is the how does this capacitance get amplified? It is because looking from this side, what will happen? If you put a voltage here, Vi, we test. So what is the current that is going to be taken out? So what is the voltage that will appear here? Minus A times
V test
V test, right? So what is the voltage drop here? 1 plus A times V test, right?
1
130.
plus A time V test.
Correct. So the voltage drop across the capacitor is 1 plus A times V test. So what is the current that is going to flow out of this voltage source? V test divided by
1 plus A time V test
1
into
plus A times SC
V test. Oh, sorry.
into V test.
Yeah, V test will get cancelled then. No,
No, I'm talking about the
no,
current.
no, no, it's okay. Okay, okay.
First of all, this
My bad.
is in this manner 1 plus A times SC, right?
Yes,
Correct?
yes.
So tell me, what is I test by V test?
1 plus A. Yes.
Correct?
Yes.
So how does this look? I mean, I applied so it looks like the capacitance here is amplified by 1 plus
1
A
plus
times,
A.
right?
Yes,
It looks na
yes,
good. And how does so basically if you look at this point and this is what is happening here also. Whatever voltage you apply at this node, it is getting first amplified at this node, right? By the
yes,
gain of the second stage, and that appears across this capacitance and that causes the current to flow here, right?
yes,
And that actually, so that is why it looks like it is a larger value of capacitance because the current requirement increases suddenly. A larger capacitance will demand more current, okay, and that is why it looks so basically this is how it behaves like a larger capacitance. It is not actually a larger capacitance, it emulates a large capacitance because of this voltage amplification, right? Understood?
yes,
Yeah. So now if you look at it, all we require is what we want to make sure that the voltage, whatever voltage you apply for for Miller effect to happen, we want to make sure that we just have to ensure that the voltage at this node is getting amplified and appears at this node, right? This is what we want,
yes.
isn't it?
Hmm.
Correct now?
Yes, sir.
Okay. And sorry. Yeah. Oof. Yeah. So all we want is that the voltage at this node is getting amplified here, right? And then that actually causes the so this is basically a feedback, right? If you see what happens is here we have a feedback of this kind, right?
Yes,
Here we have a feedback of this kind. The voltage here appears amplified here and then feedbacks like this. Okay?
yes,
So if you want the Miller effect to happen, we want to make sure that there is a feedback, and what is the direction of that feedback? In this direction, right?
Yes.
Correct. Good. However, what is the reason that the zero was appearing? Zero was appearing because there were two paths, one in this direction, one in this direction, right?
Yes.
And how were they interacting? The information, the signal is flowing from left to right, right? Correct?
Yes.
Signal is flowing from left to right in this way, and here also it is flowing from left to right in this way. So across the capacitance, if you see, signal is flowing in this direction from left to right.
Hmm.
That is how a zero is appearing. However, for Miller effect, we do not want, we do not need the signal to flow in this direction. We only need the signal to flow in this direction, right?
Yes.
So if we make sure that the signal flows only in this direction and not in this direction, then we can make sure that the Miller effect still happens, but the zero will not appear after that, isn't it? Is that point clear? I am trying to make sure that this signal information is only moving in this direction and not in this direction. So this I am trying to remove.
Okay.
So the ideally, I mean, how we will do that, we will not get into that, but idea is clear, right?
Yes.
For Miller compensation, we only want the signal to flow from right to left,
Yes.
correct? And zero happens because the signal is flowing from left to right.
Yes.
So
Yes.
if we only want the Miller effect, because that is the only thing that we want. We want the Miller effect and not the zero. So that is why you only have to make sure that the signal flows in from right to left. Correct?
Okay. Yes.
And this can be easily achieved if you simply place a
That.
not a diode, any unilateral device. So this GM is also a unilateral device, right? Whatever happens here will not affect this point, right?
Yes. Yes.
Signal can only flow in this direction, correct?
Yes.
So in this way also, if you place a some GM or some, let's say, let's call it some A, okay,
Hmm.
and this is C, M. So now what will happen? Now you can make sure that the Miller effect is there, but the zero will not be there here, okay?
Yeah.
And this idea was utilized in Ahuja compensation. So you can go back and read this, okay? All right. So this was actually Ahuja compensation.
So there's
Okay.
a problem. I mean, in
Huh?
that question, assignment 6.
Haha.
So there, we have to assume a. I mean, bias current will be there,
No, no,
and
I will come to that. I'm talking about going to talk about this next. This is clear, right? First,
yes,
this all these things that I
yes.
talked today, the compensation thing. I'll come to the bias thing to just in some moments.
So,
But this
and
is
one more thing that in previous week we have a issue with that assignment 5, question number 8.
yeah, yeah.
Where
Again, I mean, this was also raised by another person before. I am not the right person for that. See, I will not be able to help you out there because I do not look into that. This is not a part of. I'm not a part of administration. You'll
okay,
have to raise this concern with other people. I mean, the people who are there in the administration part of this who
how
look
to
after the
contact
course.
there?
Maybe you can mail the instructor, okay, or
Okay,
you can mail the NPTEL team,
okay.
or you can raise this question also in the Q&A, okay. Probably there you will be. I don't know. I mean, these are the three places that I know of. You can do all any of the three.
Okay.
Okay. All right. So this is clear, right? Whatever I talked
Yes.
about compensation. Good. So now let's quickly go into. So I guess this is straightforward, these two things, because this was covered in the lecture pretty well. So I'll go straight away into the problem. Huh. So this is the question that I think you are asking, right?
Yes.
So see, the way this is has to be dealt with it is you have this amplifier, right? This
Yes.
op amp. So in general, op amps, what Sir discussed in the lectures was that he only discussed about two non-idealities, right? No, no, he only discussed about
Offset voltage.
offset and common mode issues, right?
Yes.
So he talked about offset. That's good. But there is also another problem. See, in this is not a problem if the MOSFET, if the used op amp is implemented using MOSFETs. I mean, it's also a problem there, but it's not that big a problem. But for op amps that are implemented using
BJT.
BJTs, this is a bigger problem. So what happens is at the input, where will the input be? Input will be some BJT base, okay?
Yes.
And this BJT base, if you remember, it requires some current, IB, right?
Yes.
Base current for biasing. So there will be some bias current here, IB1 and IB2.
Yes.
So there are two unknowns already, IB1 and IB2, right?
Yes.
You do not know anything. I mean, so why I'm telling it is unknown is because even if it is mentioned, so whenever you procure a op amp from
Hmm.
the market, there will be there will be a data sheet associated with it in which these informations will be given.
Yes.
However, the manufacturer will always mention IB1 and IB2 with some plus minus something percent. Okay, they'll always give a range or a tolerance value, but you cannot go ahead with that, right? You need exact measured value, isn't it?
Yes.
So that is why these two are still unknown to you. You'll have to do some measurement. Other than this, you already know that there is also a offset problem, right?
Yes.
And you can model the offset by, how will you model the offset? You can model the offset in this manner. Sorry, isn't it? And
We
now,
can also connect the offset voltage to the negative terminal also, right?
yeah, you can do that. That's not a problem.
So
I'm just doing it.
according to, I mean, wherever we connected, the value gate changes.
Plus and minus. It will simply become. It will simply change its sign. It will not change anything else.
Okay, magnitude will be same.
Yeah, of course. Because these two terminals are identical in all sense except for their signs, right? So that is why magnitude will remain the same, only the signs will change. Got it?
Okay.
And this then is the overall. So this is something that you will get. So this is input number, input plus, this is input minus, and this is your output.
So I can assume a IB1 of current source with the parallel of minus input and IB2 of current source in positive input in parallel.
No, no, not parallel. I mean, this is what is meant by parallel.
Parallel mean IB1 connected to the, I mean, main
IB1 will not
real.
flow. One second, IB1 will not flow unless you connect anything with it. Okay.
Okay. IB1 is
Sorry.
flowing because of biasing, right?
No, 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 sorry, sorry. Yeah, you are correct. IB1 will flow always. Yeah. I'm sorry. You are right. IB1 will flow. So you have to assume something of this kind. Yes, correct. Something of this kind. Okay. And then again, you have to assume that mm, sorry, something of this kind, and yeah, okay. So this is what you have to assume. Got it?
Okay.
Right now?
Okay.
Huh. This is how it will work. Now these two are the IV1 and IV2.
So in question they asking that to that inserting 1 mega ohm resistor between inverting input gives the V not equal to 0.230. So that 1 mega ohm will be connected between IN minus and the node between R1 and R2, right?
Node between are so okay, one second. So this is how it is. So like this.
Yes.
Okay.
Okay.
And in one case it is like this.
Okay.
Got it?
Okay.
This is how you have to do. Correct?
Okay.
Yes. There's a small issue here. Mm, there's a small issue here in the modeling. Uh,
IB1 and IB2 is the input current of the op amp. If if we model this way, then
it will not. I don't think it is correct this way. So okay, this is this slight confusion here. Mm, So what you can do? So see, the thing is that what you can do is IB1 and IB2 have to assume in this manner, I think. Okay, this there is a confusion. I there's a modeling confusion here. How do you model it?
sir, if we put a resistor, like assume a resistor between minus
Yeah,
and
when the full circuit is considered, then that IV1 current source makes sense. Otherwise, in open circuit, it's, I mean, is violating the KCL also.
So this is how you have to assume actually. This is how it is. It actually appears when you have IB1 and IB2. It will actually start taking current from the input. What very wherever you apply the input. Okay. So when you say that this is IB1 and IB2, this is how it will work. They start taking current from the input like this.
So this IV2 and this offset voltage will be in series.
Yeah, what is the problem with that? What is the problem with that?
So how if this is the case, if we ground the IN plus terminal, then what will be the voltage
Hmm.
on positive terminal? How do we calculate them?
One second. One second. One second. Let's go back to that thing only. The way to do it is for if you want to find the current, what you have to do is what do we do if you want to find the current? we have to mm, so there is a confusion. I'll have to look it up. Okay, I actually don't remember how it is modeled actually. Hmm. I I have a confusion here. I'll have to look it up. I'll have to look it up how it is modeled. Okay.
Okay.
Okay, I'll come back to it in a short while. Let's talk about this quickly. There is something else here. But what I was trying to emphasize here was that there are three unknowns here, right? There are three unknowns. Two currents and one voltage, offset voltage, right? There are three unknowns here, IB1 and IB2, and so there is IB1, there is IB2, and there is also V offset, right? So there are three unknowns here. So you need three experiments, isn't it?
Yes.
So those three experiments are actually what are given here. So if you have the correct model, you will be able to solve this. I'll get back to it in this session
Sir,
only. Huh?
can I share my screen?
Why
I
not?
have the exact page number where in Bezier Trezor we they discuss the
Oh,
input bias
good,
current.
good. Please go ahead. Let me stop sharing.
One second.
Yeah, you can go ahead. Okay. Oh
But
yeah.
I have a doubt that in here also they didn't connect that offset voltage and input bias current in same circuit, so I have that doubt only.
Okay, I understand. So now I understand. So you can turn off your screen sharing.
Okay.
Okay. Yeah. You see, when you have offset, still, let's say you do not have offset. Okay. What will you do? You put a current source here, right? This is one IB1 and this is IB2, isn't it? Correct?
Yes.
Because of offset was it, what is going to happen? By the way, offset and currents are independent, isn't it? The current does not know whether there is offset, offset does not know whether there is current. Current and offsets are independent. Neither should affect the other one, isn't it?
Offset mean voltage offset, right?
Yeah. Voltage
Okay.
offset, yes. So what do you think should happen? The current is something which is going inside, independent of the offset.
Yes.
Correct?
Yes.
So where should the offset be? So by the way, this is not so where will the terminal be? Terminal will be somewhere here, right? Okay, other way. Let's draw this another manner. Is this okay?
Hmm.
This is the correct. If there is no offset, this is right, right?
Yes.
Okay. So if there is offset, what should happen?
If no current is there, then this offset will be on series with that pin.
Correct. So you just have to put it in series still. Doesn't matter now where if you put the voltage source here or here, why does it matter? It will not matter now.
Okay.
So this is actually the way. Okay. So
Okay.
let's say this is some V offset. Got it? Yeah, so I
Yes.
was not actually, I forgot this modeling. Anyway, thank you
Okay.
for sharing that. Yeah, so now you have three unknowns and three equations, I mean, three measurements also. So now you will
Yes.
be able to solve it. Okay. So the when it was said that you have to add a resistor, so basically this will be modeled in this manner, and then you also have some offset here. So where will you put the resistor? Resistor will be put here
Okay.
and here. Okay.
Okay.
Yes. Cool. Uh, I think that is so. That's it, right?
Yes.
Good. Nothing else to be spoken here. Uh, yeah, one more thing. So, what is offset current and bias current? These are the
Bias
two.
current is the average value of
Correct, correct. So, bias current is IB1 plus IB2 divided by 2, and offset is,
IB1 minus IB2.
yes, correct.
It's a modulus.
Of course, of course. You, yeah, correct. Good that you read it anyway. So now you already know that. So let's talk about this problem here. So tell me, this is an example which is very similar to the one that is there in the assignment. So first of all, tell me, what is the, is this system stable?
Yes, sir.
This system is stable?
Yes, sir.
How is the system stable?
Uh, uh, negative, negative. So the in cascade of inverter is like a latch condition for.
Yeah, so this is not a stable thing, right? This is a positive
Yeah,
feedback.
this
This
is
will not,
positive.
this is not stable at all, isn't it? This is not stable. So what you have to do is you have to connect a inverter here, isn't it? Now the system has a hope of stability, right? Now it
Yes.
is at least in negative feedback,
Yes.
correct? Okay. So now tell me, uh, these are some of the values that are given. R naught is not shown. I have not shown R naught here, but you can understand, right? This is GM, and there will be some output resistance. There is some output resistance here, right?
Yes.
So I'll just mention it anyway. This is output resistance. Yeah. So these are some of the this is GM and these are the R out. So all the GMs are identical. Everyone has a GM of 5 millisiemens, right? Everyone. Now tell me what will be the, so what will the phase margin? If I asked you could this question directly. First of all, tell me how many poles are there in this particular feedback loop.
One,
In the
two,
loop gain
three,
expression, how many
four,
poles will be
five,
there?
five, five.
5 poles, right?
Hmm.
So really bad, right? So it will be, a loop gain will be what? It will be GM divided by, sorry, GM divided by R
One.
naught plus, sorry, 1 plus, or rather GM R naught divided by 1 plus SC R naught, right?
Yes.
to the power of 5
Yes.
and into 1 over, or sorry, into R2 divided by, oh sorry, there is some issue here at the output. At this point, when you break the loop, uh, there will be a resistive division between R0 and R2 and R1. So let's assume that this R2 R1 parallel so how will this loop look like? If you break it from here, the loop gain will be, you apply something V test here and you have to see what returns here, right?
Yes.
So let's assume that this R2 and R1, these are very large compared to your R naughts. Okay, so then this will approximately hold true, and then it will be into R1 divided by R1 plus R2. So here I am assuming that R1 plus R2 is much greater than, assume the R1 plus R2 is much greater than R naught. Okay, this is the assumption. So this way I have how many poles? 5 poles, because it's a order. I mean, you are simply taking the power of 5. So it will have 5 poles, and all the 5 poles are at what location? Same location, right?
Yes.
So what do you think will happen to the stability of the system? It will definitely be unstable, isn't it?
Yes.
It will be unstable because the gain is very large. GM times R naught, if you see, what is the GM times R naught value? It is 5, right? The gain of each inverter is 5. So
Yes.
what is the total gain? Mod of loop gain, it is equal to GM times R naught to the power 5, and at S is equal to 0, it is GM R to the power 5, which is equal to 5 to the power 5. How much is that? Very large, isn't it?
Yes.
It is very large. So gain is very, DC gain is very large, and then suddenly there are 5 poles all at same position. So its body plot will look what kind of body plot will look like? So you have very large gain here, which is how much? 5 to the power 5. So if you take the log, so then it will be 20 log of 5 to the power 5. So anyway, 5 to the power 5, and then suddenly you have 5 poles all at the same location. So it will start going down like this.
Hmm.
So this will be 100 dB per decade, right?
Yes.
So it will definitely be unstable here. The phase margin will be negative. Negative phase margin means you are unstable.
Yes.
So it is definitely unstable. It is not good. So how do you stabilize the AF feedback? Tell me. How do you stabilize the AF feedback from
making one
whatever you have learned?
making one pole dominant.
Yeah, the first way is dominant pole compensation. How? So which pole do you choose?
All are at same position, so
Yeah, so it doesn't matter, right? So let's choose this one. So just make this capacitance very large, right? So how large will the capacitance need to be will depend upon the requirement. So let's say I want a 60-degree phase margin. Okay, if someone says I need 60-degree phase margin, so from there you have to go back and calculate what will be the requirement. Okay,
Yes.
if you have a dominant pole, then one thing that you know for sure is that because of the dominant pole, there will be some dominant pole, and after that it will do this. Sorry, so I mean you understand, right? It will
Yes.
start going with 20 dB per decade. Yeah. So it will after this thing, it'll start going at 20 dB per decade, and then after so basically at the point where it crosses the omega u, it will be 20 dB per decade, right?
Yes.
So from there you can actually go back and calculate what is the how you have to for 60 degree phase margin what you have to do. So this calculation is actually shown in the week 4 and 5, I think in the week 4 or week 5 tutorial that I had uploaded. Okay, you can go back and look at it. This how you have to solve this. Okay.
Okay.
Where it is
Okay.
uploaded?
It is uploaded on the YouTube channel only. It is also there. The link is also there in the Excel sheet that is shared with you.
Okay.
Yeah. So as I said, I mean, I was not here for the last 2 weeks, so I uploaded the content that covered in the last year for the same course. I was this
So
So the
this is the first class after that leave. I mean,
yeah, yes.
okay, okay,
so the link you have uploaded in that the solution is
I mean, this not a solution. I'm saying the way to tackle this
okay.
problem. I mean, how do you start with the if there is a phase margin specification given to you, then how do you start? How do you do a dominant pole compensation? What capacitance you have to choose? How do you decide that? This is there in that particular thing.
okay.
Okay,
Okay.
okay. So this is how you do. So dominant pole is covered. Now, how do you do? What will you do if I say you have to do it using Miller compensation? What will you do?
We'll put that Miller composition in the second stage.
So Miller compensation is trickier because all the GMs are same. Okay.
Hmm.
So Miller compensation is trickier, but in general, Miller compensation for this kind of circuits requires because there are 5 stages here, right?
Yes.
So in general, the Miller compensation in this kind of a circuit will work in this manner. You have to start doing Miller compensation is this way. So this is also called nested Miller compensation. Okay, is this so this is actually a different kind of a topic. This is all from research papers. Okay, so this is called nested Miller compensation. You go ahead with this. So you see the pattern here, right?
Hmm.
So this is how you do. This is called nested Miller compensation. This is how you do. So there are a lot of papers on compensation, by the way. So you can go back, and if you're interested, you can look into the literature. That's okay. But yeah, so you can also come up with a lot of other variants. So let's say you can go ahead and do Miller compensation for this stage, and then you can and for this stage you can do a feed forward thing like this. Okay, so
Okay.
that is also possible. You can do a lot of things here. You can also do this instead of doing a feed forward compensation like this. You can do simply a feed forward compensation in this manner, which is shit. Okay, you can do this. This is also valid. You see this, right? That this
It
will
has to
work.
be nested like that. I mean,
No,
if
feed
we
forward
put this,
compensation. No,
it
feed forward
will
compensation
provide
does not
only
work.
1 0, and there will
No,
be
but
5 4.
yeah, but one second. The zero location has to be make sure this will work, right? You see, the zero
Okay, okay, got it,
will always happen in this manner. It suddenly gives 20 day per ticket. You correct. Is that point
got
clear?
it, got it, got it.
Yeah. So actually, what will happen is this will not make. What this will do is this will
But
create suddenly
okay,
four zeros at the same location. Okay.
okay,
Yeah, this will suddenly create four zeros at the same location. And this is very clear, very easy to see if you look at it in terms of fast path and slow path. The fast path will activate at this point and it will suddenly become 20 dB per decade. Okay.
yes,
And how will that happen? It has to make sure that there are four concurrent zeros at this point, isn't it?
yes, got it.
Yeah. So this is also one way. So there are a lot of ways to do this. I will encourage you to go back and try the other ways also. Other than the dominant pole compensation, try the other ways also. Miller compensation and the feed-forward compensation. Okay, this
Okay.
will give you some insights. Okay, so with that, I think everything is covered that I wanted to cover. I can, yeah. So if you have anything else, you can ask, or we can just end the session at this point.
Sir, which type of software can I install to practice those things?
LT
I mean,
Spice. There's an LT Spice software.
okay, no, I actually, I mean, in to this week's lecture, sir was mentioning that there is a model you can put in the system that where every dimension will be mentioned, a dimension of the most transistor is in the IC level. So
That
that
is
type of
that. I mean, that is there in the IIT Madras website. I think. This is called PDK. Okay.
okay,
Sorry, this is called a model of particular MOSFET. You can go ahead and look at it. Professor Nagendra Krishna Pura's website. You can just explore it. There is a section dedicated to this thing.
okay.
Huh. Okay. Thank you. So, thank you for joining. Thank you for joining. With this, let's end the session. We'll again meet next Tuesday, sorry,
Sir,
Monday. Yeah,
before we sir, can you explain the difference between CMRR and the op-amp offset voltage?
of course, why not? So, CMRR is common mode rejection ratio. As it was explained in the lecture also, what happens is you have this is a differential amplifier, isn't it? You
Yes,
want your op amp to only act on difference between the inputs. You do not want it to act on the common mode, isn't it? And the
yes,
reason for it is that this actually comes from the application point of view. See, people do not want the common mode to be a part of the signal. It's because in general, if I talk about a certain application, so op amps are generally used in places where its most critical application is in sensing application. Okay, as it was also explained in the lecture also, there's a photodiode and then there's a detector, right?
yes,
It
yes,
senses a current, transimpedance amplifier. So the main very important application of op amps is generally in the sensing application where you have to sense really small values, okay, really small differences. So what happens is, how does sensor work? Sensor has some general stable condition, right? But if there is a sudden, if there is a small disturbance somewhere, sensor has to catch that. So what is a disturbance means? It means that there is some base point, and after that there is a difference, right?
yes,
So by definition, a sensor has to sense a difference, isn't it? It always has
yes,
to sense a difference with respect to some common mode, isn't it?
yes,
So, and it is very in any practical scenario, this common mode will be really high. Okay, let's say you are sitting on a mountain. Okay, and then you have to not so what I'm trying to explain here is that um, this is like uh, this is like you're trying to resolve a difference between so what I'm trying to say is the common mode is really high, and on top of that the difference is really small, so you have to resolve the difference, you have to sense the difference sitting on the really large common mode. So this is like resolving two very small, very closely spaced things which are really far apart. And something like that you can this is an analogy in the optical telescope kind of a scenario. So let's say two things are really close, and they are really far. So difference is very small, but the baseline is really large. So you have to actually reject the common mode, but you have to sense the difference. Are you understanding what I'm saying?
yeah.
This is a general problem in sensors. In all the sensing applications, in general, the common mode is really high. By common mode, I mean the voltages. The common mode voltages will be very high, and on top of that, there will be really minute
The
small
biasing
differences.
voltages and
Yes, something like that. The biasing voltages or the system which is preceding the op amp, which is placed before the op amp, which is giving the signal, which is giving a disturbance, that may also have some output voltage of its own. Yeah, in general, it is bias voltage. Yes. So bias voltage will be really high, and the difference will be very small. So that is something which you have to sense, and that sensing is very critical, especially if your common mode is also changing. If the common mode is not something which is going to be fixed, right? It will also change. So now if the common mode is really high, it changes. You can imagine, right? And on top of that, there is also small difference. So common mode is also changing, and also you have to sense that small difference. So that is why the common mode ejection ratio is really important. It gives you a sense of how uh, robust your op amp is to uh, uh, sensing a differential voltage in the presence of a large common mode voltage.
Can I mean, explain with some order of value, then
Yeah,
will
it's
be.
it's in generally, so people try to hit like 100 dBs and all, common mode ejection ratio, which means that if there is a even if there is a your differential voltage is, let's say, 100 dB lower than the common mode excitation, even then your system will pick up the difference. You see, and 100 dB is really large, right?
Yes.
It's like how much? 10 to the power 5, right? 1 lakh. So even
Yes.
if your difference is like 1 lakh times smaller than the common mode excitation,
Hmm.
it will still catch. So that is what people target, so sensing application, right?
Okay.
So the inventor-based question that you are telling about, that the concept of that
Ha,
question,
yes.
I think it's not that in that video
No, no, it
that
will be there.
it's about like 1 minute, like 1 minute. So it's just a discussion. It's not a solution.
No, no,
You
no,
know, it's
I
not.
have no. I will not. So what I'm saying is that I have not exactly solved it. So I cannot exactly solve this question for. I'm saying that in the 3 and 4 week 4 and 5, I have solved a question which is which looked somewhat like that. I mean, if you are given the spec of what is the phase margin that you want to achieve, from there you can go back and calculate what is the capacitance on all those things. So that is what is discussed.
Okay.
Yeah. Yes. Anyway, so yes, you understood, right? What is the common mode ejection ratio, and
Yes.
what does this mean? Yeah, and offset means that in general the two inputs that you assume to be very same, in this case Vn and Vp, right? You assume that
Yes.
Vn and Vp are identical in all sense, but that will not happen. They will not be identical. Okay, there
Yes.
will be some difference because of the, let's say, if you are using MOSFETs here, there will be some mismatch in the, let's say, in the threshold voltage. So if
Okay.
there is a small difference in the threshold voltage, then that will look like there is a difference voltage applied, right? If there is a mismatch between the two inputs, it looks like how? What does it look like? It looks like at one input you have applied an at one side of the op amp you have applied certain input, right? That is what it looks like. If you have a mismatch, so that is why it is modeled in terms of this voltage source. Are you understanding what I'm saying?
Mm, no.
Okay. So what I'm saying is, if you have op amp like this, you have two inputs. You assume that these two inputs are same, right?
Hmm.
But in general, there can be some mismatch between the two inputs. For example, if you use MOSFETs to make the two inputs, so this is something which that you will learn later. But this is an let's say this is an input stage, and let's say this is the RL. So this is one op amp. Okay, let's say this is an op amp.
Hmm.
So now you say that these are both W by L, W by L, right?
Hmm.
Same MOSFETs. However, in while manufacturing it, it can happen that the threshold voltage of these two MOSFETs will be slightly different.
Okay.
Let's say they are different by 1 millivolt. Very
Hmm.
easy. 1 millivolt is very easy to that there can be a 1 millivolt mismatch. It is very easily possible while manufacturing.
Okay.
If the threshold voltage has 1 millivolt of difference, what does it look like? The current of a MOSFET or anything that MOSFET does is always dependent upon VGS minus VTH, right?
Yes.
So if VTH has 1 millivolt of difference between the two MOSFETs, it look like that the one MOSFET that it has already 1 millivolt of input applied to it,
Okay.
right?
Got it.
So that's what. So this is very this is not a good scenario because your op amp is supposed to sense the difference, right? But
Yes.
there is already a inherent difference between the inputs of the MOSFET inputs of the op amp. So op amp has to work even in the presence of those mismatches.
Okay.
Earlier, you assume that both the inputs are same for the op amp, and then you
Mm,
were giving a difference to the input of the op amp, and that op amp had to sense. Okay, but
yes.
now in uh, even if you don't apply anything at the input of the op amp, even if you do not give any difference at the input, still there is some difference already present at the input. That is not good
Yes.
now
Yes.
because then you can make a erroneous decision, right?
Yes.
So that is critical. So there are techniques to remove the effect of these offsets. I mean this will be discussed later. I don't know whether this will be discussed in this particular course or not, but if you take a high level course, you can discuss and can learn about it.
What are the higher level codes after that analog IC design?
This will there are so in NPTL I don't know. Okay, I
Okay.
don't know
In
in
general,
NPTL.
I mean, which type of books or something?
No, this will be
No.
covered in the in Razavi's book, I think. This technique is called chopping to remove the effect of mismatch offsets. Okay,
Okay.
you can look it up. Chopping. So we just tried it. It's called chopping.
Okay.
Chopping. Okay.
Is there, I mean, when this chopping was done, is there some kind of register being used and it will be done like that? I mean, just
No,
asking.
no, no, no. Chopping is way simpler. So I'll not go into detail of this
Okay,
because
okay.
this is
It's okay. It's
yeah.
okay.
Chopping is way simpler. Even this you'll understand if you simply search for it in any book.
Okay.
It
I'll
is
look
very
at it. I'll
simple to
look at it.
understand. Huh. Okay. So now let's conclude. Fine. We'll see
Yes.
again. We'll meet again next week, same time, 6 to 8, Monday. Okay.
Okay.
Okay. Thank you for joining.
Thank you.